In this lesson, we will cover, I should say day 5, right? In this lesson, we will cover the CMOS inverter. And so we're going to use what we learned about MOSFETs in the last lesson to think about how we get logic gates and the NOT gate in particular. So to start off, let's review the MOSFET from last time. So we have this device. We have a P-type body for an NMOS and N-type corners. We call it NMOS because the thing that's going to flow is N-type charges, electrons. If I apply voltage to the gate, I'm going to push away the other positive charges. That creates an inversion layer where the electrons can now form a channel. Because I formed a channel, when I apply a voltage, I can now get current that flows. If I don't apply that voltage at the gate, then the gate is closed, there is no channel, and current can't flow. If I do apply that voltage to the gate, then the gate is open, and current can't flow. Now for a PMOS, you have to do the opposite thing. You have to go to a low gate voltage. A low gate voltage pushes away the electrons in the N-type body and creates a channel for the P-type positive charges. So that when I apply a voltage, current can flow. So the effect is the same in that we open the gate and we get things that flow, but the difference is for a PMOS, we have to apply a negative voltage at the gate. For an NMOS, we have to apply a positive voltage at the gate. Okay. Now there's nuance to that. It's actually the gate minus the source voltage that matters and some other things. But high level, you need something negative at the gate for a PMOS, something positive at the gate for an NMOS. Okay. So that's really the main point to take away from lesson. The details about semiconductors you can review. The YouTube video is posted, but that's the detail that matters. So just quickly, these review questions so we're all clear. With a high gate voltage, is the channel open or closed for a PMOS or an NMOS? So high gate voltage closes a PMOS and it opens an NMOS. If the gate is open for a MOSFET, does current flow or does it not flow? Pretty easy. If the gate is open, current can flow. If the gate is closed, current cannot flow. And we have a name for things that make it hard for current to flow. That's a resistor, right? Hard current flow means lots of resistance. And so we typically say that transistors that are on act like small resistors. Transistors that are off act like big resistors. So we're going to go away from this analog picture of kind of the amount of current that can flow to a picture of it is on or it is off. We're going to think about digital from now on. And let's just go through each of these examples. So first, the example on the left. An NMOS with a high gate voltage means that the gate is open. So that means that current can flow easily. And so that means it acts like a small resistor. Okay, so for example, V over R with R equals 1 ohm and V equals 5 volts gives you 5 amps of current. A PMOS with a high gate voltage has a closed gate, so it acts like a big resistor because current can't get through. An NMOS with a low gate voltage also is closed, current can't get through, it's a big resistor, like 10 to the 6th ohms. And a PMOS with a low gate voltage has an open gate, and so it acts like a small resistor. So that's sort of the summary of all of this. Yeah. So now let's go to the picture of circuits with MOSFETs. So in this circuit, we have 4 parts of the transistor that correspond to the 4 parts up here. Keep in mind, these arrows on this diagram correspond to the direction of conventional current flow. So starting with the NMOS, this is an NMOS transistor. Notice how electron flow is from this direction, from left to right. That means current flow, as drawn in this diagram up here, is from right to left. So in other words, D is here, S is here, and G is here. Okay, and that's exactly what we're going to see. B refers to the body or the bulk of the transistor. Generally speaking, this is connected to the source directly, but sometimes people do different things, and so it's important to know that it exists. But generally, we'll consider transistors or MOSFETs as a 3-terminal device, not a 4-terminal device. So in this component, which way does current flow for an NMOS? well, we just established is drain to source, and for a PMOS, it's source to drain. Again, don't get confused by the naming. Things in general go from source to drain. But when we think about conventional current, you have to flip it for an NMOS because the things that are flowing are electrons, whereas in a PMOS, things that are flowing are positive charges, or rather holes and lack of electrons, but bubbles. So for an NMOS, it's D to S. For a PMOS, it's S to D. Now, for MOSFETs in diagrams, we generally draw current going from top to bottom. That's just convention. And so the drain will be on top for an NMOS, and the source will be on top for a PMOS. If you see an arrow on this component, the arrow is typically drawn on the side with the source. Okay. So here you can see on the NMOS, the source is on the bottom, that's where the arrow is. On the PMOS, the source is on top, so that's where the arrow is. The authority for what kind of transistor it is wherever the arrow is. If the arrow is on top, you have a PMOS. If the arrow is on the bottom, you have an NMOS. And then you figure out which one's S, which one's D, which one's G. Now, sometimes MOSFETs are drawn with the diagrams on the right. I don't like this notation, so if I ever use this, I'll make sure to give you an arrow. But here it's implicit that current is flowing downwards. And so you have to figure out yourself that since current flows downwards, that means for the PMOS, S is here and D is here, whereas for the NMOS, D is here and S is here. That's your job to figure out, with the key distinguishing factor from an NMOS to a PMOS being the circle that you can see. That's what we use. And it sort of gets like a NOT gate. It has an inversion bubble there. This is the same sort of logic. So let's do a quick check. What type of MOSFET is this? This is a PMOS. You can tell both due to the inversion bubble, but also due to the fact that the arrow's on top. Where's the gate? Where's the drain? Where's the source? Well, right there as labeled. If it's a high voltage source, how much current flows? Well, think, if it's high voltage, that means the positive, if it's a high gate voltage, that means for a PMOS, the gate is not open, right? Positive voltages at the gate are going to not push away the negative charges that make up the body of the transistor. Go back here and see that. Go to PMOS and reset. If I have a high gate voltage, I'm not pushing away the negative charges. I need a low gate voltage to push away the negative charges. So not much current flows with the high gate voltage. And so if I replace the S to D path with a transistor, with a resistor. In other words, if I get rid of this transistor and just want to put a resistor from S to D instead. What size resistor should it be? It's going to be a resistor that's very large, 10 to the 6th, because the transistor is off. It's letting through very little current. And because it's letting through very little current, it acts like a big resistor. Now, if the voltage source is low, then the PMOS is on, lots of current flows, and the transistor acts like a tiny resistor. So that's the picture of thinking about transistors like resistors. Now let's take that one step further. Instead of saying tiny resistor, we're going to say short circuit, right? A tiny resistor allows a lot of current. A wire, a short circuit, allows all the current. And instead of saying big resistor, we're going to say open circuit. A big resistor allows very little current, and an open circuit allows no current at all, right? So let's test the two possible inputs to this below circuit. But before we do that, let's identify which one's the PMOS and which one's the NMOS. Well, PMOS is on top and the NMOS is on the bottom. Okay. So if I input a 5-volt input, which is on and which is off, high means that PMOS is off and NMOS is on. So the PMOS is going to act like an open circuit because it is off. The NMOS is going to act like a short circuit because it is on. Take a second and just think about what I said and internalize that. So the PMOS is off and the NMOS is on. And the PMOS being off means that it acts like an open circuit, and the electrical path exists from Vout to ground. Okay? So we input a high, maybe 5 volts, and we get out a low, 0 volts. Now let's look at the other situation. If I input a low, 0 volts, then the PMOS is going to be on and the NMOS is going to be off. And so the electrical path is going to exist from Vout to 5 volts. So we input 0 volts and we get out 5 volts. This is an inverter, right? Our two inputs are get high or input high, get out a low. Input low, get out a high. That is a NOT gate. And this operation of inversion is not something we can accomplish in any other way. I encourage you to try it. Try with just diodes or simple circuit components that don't involve transistors. You won't be able to get this CMOS inverter effect. It's something very special to transistors, and it's what makes them so useful. And it creates a NOT gate, right? So that's our fundamental object, the CMOS inverter. Everything else we build is going to be off that. So let's quickly use a demo just to demonstrate what we just talked about. So notice we have two inputs here, or we have one input. Okay, these are both the same input. They're coming from A. And I toggle A with this switch right here. So if A is off, which it is right now, then the PMOS is open and the NMOS, sorry, PMOS is like on and the NMOS is off. And so that means the path exists from the output to 5 volts, VDD, 5 volts. Whereas if the if I turn off A, then the PMOS turns off and the path exists from the output to ground, 0 volts. Okay, so that's the CMOS inverter. Now we can make other logical operations too. In particular, NAND and NOR are going to be the two operations that we can make with MOSFETs as well. So a NAND gate, I'm going to put two PMOSs in parallel. So now we have two inputs. We have B and we have A. Okay, these two are PMOS. And these two are NMOS. Okay, so the two PMOS in parallel. If I turn A on, well, a path still exists from this wire to 5 volts. I'll call it that. This path still exists. If I turn A off and turn B on, well, the path still exists through here. If I have both of them off, the path still exists. I need to have both of these PMOS transistors off so that the path exclusively exists. Let me erase these green markings. So that the path exclusively exists from the output to ground. Okay, so this is I encourage you to play with this tool yourself. It's hard to describe, but I think it'll be very intuitive to use if you play with it yourself. But the point is, from this, A and B both have to be 1 to get out a 0. That's an AND gate, or sorry, that's a NAND gate. You can see the same logic for a NOR, and so you should fiddle with this yourself and see what you can get with it. So the other logical operations that we have available to us are this is the complete set of logical operations that we have available to us. We have AND, we have OR, we have NOR, NAND, XOR, and XNOR. Okay, so let's go from the top. AND is going to be A and B need to be 1. So we need 1 and 1 gets us 1. But if they both are not 1, we will get 0. A and B have to be 1. We create an AND gate by putting a NOT gate after a NAND gate. So NAND is what we just showed here. I'll talk about it now, actually, or in a second. So I'll get back to the compound gate. Sorry. The OR gate is A or B has to be 1. So they can both be 0, then you get out 0. Or you could have 0 and 1, 0 with 1. That gets us 1 because 1 is my God. Let me try that again. A or B needs to be 1. If B is 1, then we get out 1 no matter what. If A is 1, then we get out 1 no matter what. If both are 1, fine, we also get out 1. Only when neither of the inputs are 1 do we get out 0. Okay. Now, NOR and NAND are exactly the opposites. Notice row by row, it's exactly the opposite for each of these, for Q, and Q represents the output. Now, the reason that NOR and NAND are quite important is because NOR and NAND are easier to make than and OR. AND and OR require the NOT gate after a NAND and NOR. But a NAND and NOR you can make with only 4 transistors. You need more transistors to make the other ones. So that's why NAND and NOR are important. To actually make AND, you just put a NOT gate after a NAND, right? So that gets us the functionality of an AND gate. To make an OR gate, you put a NOT after a NOR gate. And so that gets us the functionality of an OR. Now, the last two to talk about are XOR and XNOR. X means exclusive. So only one can be 1 or 0 for these two gates, right? So for XOR, it outputs 1 if A only or B only is 1. If both of them are 1, then you get 0. Only one of them can be 1 to get the output of 1. Otherwise, you get 0, right? That's this exclusivity here. In these two rows, only one of them can be 1. XNOR is exactly the opposite of that. Only one of them can be 1 to get a 0. If both of them are the same thing, then you get 1. And so to make an XOR and XNOR, they're a little more complicated and they're kind of composite. So to get XOR, you need 5 gates. And we can even count the transistors that to here, and you'll see it's, I think, going to come out to be 4 plus, I think, 16, like 22 transistors total for this full circuit. I think you can make it with a more complex architecture and some triple input gates. But my point being, it does look more complicated, but it still just comes down to MOSFETs at its core. It's still just transistors under the hood. And you can see if I input 1 and 0, then I get 1 out. If I input 0 and 1, then I get 1 out. But if they're both 0, then I get 0 out. And if they're both 1, then I also get 0 out. And you'll see that XNOR has the opposite. So yeah, that's our complete set of logic gates. So we're going to abstract away from thinking about the transistors now. We're going to focus on the logic gates moving forward. But I encourage you to really understand how each of these logic gates comes from the MOSFETs. If you can understand that, you have a really good understanding of MOSFETs. So that's that. Thank you.